In this video, we're going to study the dissolving process. So to dissolve a solute, there are a few steps that are needed. The first thing you need to do is you need to break the solvent-solvent intermolecular forces. So for example, over here, we can see that all the solvent particles are attracted to each other because of their intermolecular forces. So for example, if that solvent is water, then all the water is held together by hydrogen bonds. Now here we have the solute. You'll notice all the solutes are held together by forces as well. So you need to break the solute-solute intermolecular forces. So for example, if this was sugar particles, then maybe I'd have to break some dipole-dipole interactions there to separate them. Or if it was an ionic compound, I might have to break the ionic attraction to separate them. Either way, you need to separate the solute particles from each other and the water particles from each other. And then afterwards, you need to create intermolecular forces between the solvent and the solute. So here's my solvent, here's my solute, and intermolecular forces form between them. And now I've formed a solution, and that's the dissolving process. So the dissolving process involves breaking the solvent-solvent intermolecular forces, the solute-solute intermolecular forces, and then forming solvent-solute intermolecular forces. And for that to happen, the solvent-solute attraction has to be greater than the solvent-solvent attraction. So basically, there needs to be a reason for the solvent to want to attract to the solute. If the solvent-solvent attraction is too strong, then the compound just won't dissolve. But if the solvent-solvent attraction is not very strong, then you can have the solvent-solvent attraction break, and the solvent and solute can essentially be attracted to each other. So let's discuss water as a solvent. Water is a very good solvent. It's the solvent we'll be studying the most in grade 11 chemistry and for a big chunk of chemistry going forward if you decide to pursue chemistry in the future. Water is sometimes called a universal solvent. And that basically means it's a really good solvent. It can dissolve a lot of things. Remember that in chemistry, molecules can be non-polar molecular, polar molecular, or ionic. And remember that the general rule of thumb for dissolving stuff is that like dissolves like. So typically, ionic and polar solutes will dissolve in polar solvents. So for example, salt and sugar can dissolve in water because water is polar. Salt is ionic, sugar is polar. And nonpolar solutes dissolve in nonpolar solvents. So for example, the oil and water will not mix together because oil is nonpolar and water is polar, or grease in oil that's nonpolar. So remember that water is a polar molecule. And so what that means is it can dissolve both polar covalent compounds and ionic compounds. Water cannot dissolve nonpolar compounds. So we call water universal because it is a really good solvent. It can dissolve quite a few things. For example, the polar covalent and the ionic compounds. The term universal usually leads you to think that it can dissolve anything, but that's not really true. There are things it cannot dissolve. For example, non-polar compounds it cannot dissolve. And there's other things that have pretty low solubility in it as well. But regardless, it's still a good solvent because it's a polar molecule and has those partial positive and partial negative charges that can interact with partial charges of the polar compounds and full charges of ionic compounds. So here we have a summary of the like dissolves like rule. Remember that if your solvent is polar, typically you can dissolve polar solutes, and you can typically dissolve ionic solutes. If your solvent is nonpolar, usually you cannot dissolve polar and ionic, and you could dissolve nonpolar though. So nonpolar dissolves nonpolar, polar dissolves polar / ionic. So let's go a bit more into why water is such a good solvent, such a great solvent. And really it's because water is strongly polar. Remember, water has the ability to do hydrogen bonding. There's a big electronegativity difference between the oxygen and the hydrogen of a water molecule. So because there's such a large electronegativity difference, they still share. It's just that the share is so uneven that the oxygen gets its partial negative and the hydrogen gets its partial positive. And so that's reviewed from some of the Unit 1 material you saw before. Just a quick reminder, remember the electronegativity difference is the difference in electronegativity between the two bonded atoms. So we can see the two bonded atoms here. And remember that when you're looking at electronegativity, or when you're looking at polarity, you look at the difference in electronegativity of the bonds, but you also look at the shape. And so the 3D shape based on VSEPR has to be taken into consideration. And the general idea we saw is that for a bond to be polar covalent, it had to be larger than 0.5 and smaller than 1.7. So both bonds in water are polar covalent, and the shape makes it such that the molecule overall is polar, with the partial negative on the oxygen, partial positive on the hydrogen. And as a result of that great polarity, water can do hydrogen bonding. So water can be attracted to a whole bunch of different particles as long as there's full charges or partial charges on it. So you can see the water molecule with its partial charges over here. You can see water molecules doing some hydrogen bonding over here. And remember that hydrogen bonding is between a partial positive oxygen of one water molecule and a partial negative hydrogen of another water molecule. And it could also exist whenever you have HF, NH, and OH. But right now we're really focusing on the water aspect. So here we can see different images. We can see water dissolving an ionic compound, specifically NaCl, and we'll see more of that, more detail of that later on. But the idea you can see is that partial positives are surrounding negative ions, and partial negative oxygen is surrounding the positive ion. And then here we can see water dissolving a molecular compound that happens to be polar. So you can see we have water over here, and you can see we have the molecular compound over here, and there's some hydrogen bonding happening between the water and the polar solute. So we can see water dissolving molecular compounds as well, and that all has to do with its ability to hydrogen bond, which is due to its polarity. And so in the next video, we're going to take a look at how this dissolving process works for ionic compounds, and then we'll take a look at how the process works for molecular compounds as well. To summarize, in this video, we saw that the dissolving process involves breaking intermolecular forces between solvents and between solutes, and creating intermolecular forces between solvent and solute. We saw that water is a really good solvent. It's universal. We reviewed rules such as like dissolves like. Basically, polar dissolves polar and ionic, and nonpolar dissolves nonpolar, but cannot be dissolved in polar. We saw that water is called universal, but can't really dissolve everything. It can only dissolve really polar and ionic, but that's a lot of compounds regardless. And then we also saw that water is a really good solvent because, well, the reason for it is that it's polar. And the fact that it's polar means it can do some hydrogen bonding and interact with a lot of substances as long as they have some partial charges or full charges.